In this video, we're going to take a look at number 12 on practice exam 3.1 in the fall 2021 semester in Chem 1211. And this problem is all about lattice energy. The question asks, which ionic compound is expected to have the most negative lattice energy? And we've got a series of ionic compounds with various positive and negative ions involved. Now, let's talk about this most negative for a second. The convention built into this problem and built into Chem 1211 as of this recording is that the lattice energy is the energy released when the ions in the gas phase, let's call them M plus for the cation and X minus for the anion, although they need not have unit charges like this. When these ions come together and form a solid lattice Mx, there is a massive amount of energy given off. That is the lattice energy, typically in kilojoules per mole is how it's expressed quantitatively. Now, for the purposes of this problem, we're not going to calculate anything, but the thing we do need to understand is that structure influences lattice energy in a predictable way. Structure dictates function, right? A very broad, very important idea for Chem 1211 and 1212. And the way structure influences lattice energy is beautifully encapsulated by Coulombs Law. Now, Coulombs Law we can express in equation form, and we're going to write an equation here, but we're going to use it for qualitative understanding of which lattice energies are more or less negative. According to Coulombs Law, the lattice energy is proportional to a ratio. The products of the two charges, let's just say Q plus for the charge of the cation and Q minus for the charge of the anion with the negative sign included, divided by the distance between the centers of those ions. Now, the way we've written it here, this will be a negative value since Q minus is less than 0, it's a negative charge, and Q plus is a positive charge. So, although this equation is actually not useful for calculating anything, because it's just a proportionality, it can tell us qualitatively what causes lattice energy to become more negative or less negative, more exothermic or less exothermic. For example, increasing the magnitudes of the charges, going +1 to +2 to +3, that's going to increase the magnitude of lattice energy, make lattice energy more negative, more exothermic, we would say in a systematic way. Decreasing the size of the ions, moving those centers closer together, decreasing R, that's going to influence lattice energy, and decreasing R is going to make the lattice energy more negative. And the reason for that is R gets smaller. This ratio gets larger in magnitude, but the numerator is negative, so the number gets more negative, right? This is just a quantitative explanation of what's going on here, but the intuition is important. Smaller ions and higher charge are associated with high lattice energy. Now let's take a look at the compounds we're dealing with and make a list of them and get a handle on the charges and the relative sizes of the ions involved. So we have NaCl, NaBr, we have Na2O, we have MgF2, we have CaO, and finally we have MgO. Now, one kind of tip or trick for lattice energy problems is to appreciate that charge has a much bigger influence on the magnitude of lattice energy than ionic size. Ionic size doesn't change that much, not nearly as much as charge, and going from +1 to +2 to +3, for example. So think about the charges first. Thinking about charges first will allow you to rule out some ionic compounds that clearly don't have the most negative value of lattice energy. So let's just lay down the charges for each of these. I'll put the cation on the left, +1, +1, +1. So in Na2O, we're only concerned with the charge of one of those sodium cations, +2, +2, and +2. And then on the anion side, we have -1, -1, -2, -1, -2, -2. And if this is not something that you can do quickly, I would encourage you to make some notes on your crib sheet about how group number on the periodic table relates to the charge on the most stable monatomic cation or anion for a particular element. So now that we've done this, we can refer back up to the equation above and note that the +2, -2 compounds are going to have much more negative lattice energies than the others, right? So immediately we can kind of rule out NaCl, NaBr, Na2O, which has a +1 cation, and MgF2, which has a -1 anion. And it comes down to CaO versus MgO here. Now, calcium versus magnesium. Let's check them out on the periodic table. Magnesium is above calcium. Calcium is larger than magnesium. The smaller of the two ions is going to be Mg2+. And let's make a note of that Mg2+ is smaller than Ca2+ rather. And so the big winner here in terms of the most negative lattice energy is MgO. With that smaller ionic size, we're going to get a smaller R value there. That will make the lattice energy more negative. MgO is our most negative lattice energy within this series.